So today we'll start new topic. New topic is circular motion, uniform circular motion. So we know from Newton's second law, or Newton's first law, I should say, if an object is moving with some velocity, and if there is no force acting on that object, so the object will keep moving in straight path. Okay? So it will keep moving in a straight path unless and until there is an external force acting on the object. So let's say you have some object . Give me a second, let's see if I recorded this or not. Okay. So here you have an object moving in a straight path, okay? So let's say you want to keep this object in a circular track, okay? While this object is moving in a straight line, you want to constrain the motion in a circular track. So how do you do that? So to keep this in circular track, you need to pull that object, okay, towards the center. To keep the object in a circular track, you need to apply some kind of force that keeps the object in circular track. And if you remove that force, then the object will just move in a straight path. Okay? So for example, you are rotating some kind of an object tied to a string. Okay, so that's the object rotating in a circular track tied to a string. So what keeps the object in this circular track is the tension in this string. Okay? If you cut the string, what will happen? The object will just fly off in a straight path. Okay? It will move in a straight path. So the force that keeps the object in the circular track or circular motion is the tension in this case. So in the same way, in different kinds of circular motion, different kinds of forces keep the objects in circular track. Okay, so we need to identify what kinds of forces keep the object in circular track. So that's the main theme of this topic. Okay, so I will write it here. So which force keeps an object in a circular track. So this is what we want to identify. Oops. And we know that if there is force that is keeping the object in the circular track, then there must also be acceleration. And we know that the force is pointing to the center of the circular track, right? So the object is moving this way and we are pulling it inside. That's why it's in the circular path. So the object tends to move this way, but we are pulling it inside with the force that keeps the object in the circular track. So at this point, the object tends to move this way, but we are keeping this object in circular track by pulling it inward. So at each end point along this path, we are pulling it inward. We are pulling it inward. Okay? And because of that, the object remains in the circular track. So this force that keeps the object in circular path or circular track is called centripetal force. Okay? Because it's directed to the center, so it's called centripetal force. Centripetal force. And again, I said when there is force, there must be acceleration. And the acceleration is also pointing in the direction of the force. And this acceleration is called centripetal acceleration. Okay? So the acceleration corresponding to the centripetal force is called centripetal acceleration. which is given by this formula. So centripetal acceleration is given by v squared over r. And if I ask you what is the centripetal force, what would be the formula? If that's the acceleration, what would be the force?
Mass times.
Yeah, exactly. So force is mass times acceleration. So mass, acceleration is this thing, v squared over r. Okay? So this thing gives us the force, and this thing gives us acceleration. So how do we know the acceleration is pointing inward? We know that conceptually, but can we show that vectorically also? So let's look at that. Draw some vector and see if we can prove that using the vector diagram. So let's say we have a circle. Let's see if I can draw a circle. Okay. So object is at this point. So the object is at this point. And at this point, the velocity of the object is tangential to that point. Okay, so the velocity points this way, straight down. Okay? So that's the initial velocity. And when the object reaches here, so it's moving this way clockwise. Okay? You're rotating the object clockwise in clockwise direction. And at this point, the velocity would be tangent, so it would be that way. Okay, so that's v2. So at each and every point, you can draw vector, velocity vector. So if you consider this point, then the velocity would be tangent at that point, that way. Okay. If you consider, let's say, this point, then the velocity would be tangent at that point. Okay, so like that. So that's the velocity. So velocity is always tangent to the circle. So we know the acceleration is defined as v2 minus v1 over delta t. Okay, that's the definition of acceleration. So if we know v2 minus v1, then we also know a. Okay, in other words, if we know the direction of this, then that will give us the direction of a, because time doesn't have direction. So direction of change in velocity is the direction of a. So let's find the direction of this difference in velocity. So we have two vectors. We want to find the difference. So v2 this could be written as plus minus v2. Okay? Same thing as that. So I want to add v2 and negative this is v1, negative v1. So that will give me this change in velocity. Okay? So v2 is that. And to add negative v1, negative means I need to flip this. Okay? Negative means opposite direction to that. So flip that. So that would be negative v1. And then I want to add this v2 and v1. So we learned about the vector addition rule, if you guys remember. So you place the tail of the first vector, this vector, to the head of this vector to add. Okay? So just transport this in such a way that this tail is on the head of the first one. That's to add, okay? So that's negative V1. And to add, you connect the tail of the first one to the head of the second one. Okay? So this would give you V2 plus minus V1, okay, which is V2 minus V1. So you see that difference? Which way is the difference pointing? The difference is pointing to the center. You see this difference vector. Okay, that's pointing to the center. And you can do that for all the different vectors. No matter where you find the difference would always be pointing to the center. Okay? That's why this acceleration is called centripetal acceleration. Okay? So A is given by V squared over R. I mean, we can prove that, we can derive this equation, but that's a lengthy one. We don't need to do that. We'll just use the formula. Okay? So with that, now we can solve worksheet 9 problems. So if you guys are on Zoom, you can download worksheet 9 from Blackboard. So let's look at problem 2. So please read problem 2. So the car is moving on some kind of circular track. We have a circular track, and the car is moving on that circular track. Okay. So the car tends to move straight this way, okay, at each and every point. The car tends to move straight. But what is keeping the car in the circular track? Something must be keeping the car in circular track. Something is pushing the car this way. Something is pushing the car this way. That prevents it from moving in straight track. The car doesn't go this way or this way. It's in this track. So something is keeping it in this track. What is that force? In this case, that force is the friction of the tires. Okay? The car's tires provide this push force, okay, towards the center, and that keeps the car in the circular track. Oops. So this thing is very sensitive, so if I touch it. Okay, so here the car's tires keep the car in the circular track. It's a circular motion. Okay. Or you can say that is the, I should say, there's the friction of the tires provides the centripetal force necessary to keep the car in the circular track. Now, this is very important. Is the friction force static friction or kinetic friction in this case? It's a very tricky one. Is the friction static or kinetic? So the friction is in this direction, okay, not in this direction. There is also friction along this direction, but that's not what we are looking for in this case. We are looking for the friction in this direction. And this friction is is static friction, okay, not kinetic friction. In order for you to have kinetic friction, the two things must be sliding over each other. Okay, so one must be going this way, and the other one must be going that way. So there must be some kind of like relative motion. But here, there is no relative motion. The car is intact to the track. Okay, so there is no relative motion between the car in this direction and the road in this direction. So it's the static friction that is keeping the object in static in the circular track. Okay. So it's the static friction, not kinetic friction. Okay. So to get maximum speed, there must be maximum friction force so that it doesn't slide. Maximum friction force. In this case, it's again static friction. Okay. So we can write Newton's second law for this case. So let's consider this is our car. Okay, Newton's second law. So that's the normal force. That's mg, weight, and there is this friction force pointing to the center. Okay. So that's the Newton's. That's the free body diagram for that car. So sum of forces along x direction is 0. Again, because there is no relative motion. Okay, the car is not sliding. This won't be 0 if the car is sliding. This is 0 because car is not sliding. It's intact to the road. And that's the reason we are using this static friction. Okay. So what are the forces along? Oh, sorry. I take it back. So there is this friction. There is this mass times acceleration. There is acceleration in this case actually. Okay. The acceleration is pointing to the center. So this is centripetal acceleration. Okay. So what is the force along x direction? Static friction, right? And that is equal to m times AC. Okay. So here, this m, AC is v squared over r. This is the centripetal force, and it's provided by the static friction. So I mentioned this in the very beginning that the main theme of this topic would be to figure out which static friction is providing, or which force is providing the centripetal force. Okay, in this case, this static friction is providing the centripetal force. So if we want maximum velocity here, then the friction needs to be maximum. Okay, so F max is equal to m v max squared over r. So what's the question asking us? The question is asking us to find the maximum speed. Okay, so we want to find this. So how do we find that? We don't have this. But we know the formula for this. What's the formula for that? Fs max. You should know that. We used that in lab last time. What's the formula for Fs max? Mu s times n, right? That's the formula for that. mv squared over r. Now we don't know normal force. Is there any way we can figure out normal force from free body diagram? You should know that from previous numerical problems. So along this y direction, there is no acceleration. It's not moving up or down. So that means n minus w would be 0. So that means n would be w. And w is m times g, mass times acceleration due to gravity. Okay, so we can replace this n by mg. So mu s, n is mg, is equal to mv squared over r. So you can cancel m and m on both sides. And then you can write the expression for v. So what we have, mu s, m is cancelled, so mu s g is equal to v max squared over r. So multiply both sides by r, this r and this r cancel. So v max squared is mu s rg. We want v max, so you need to take square root on both sides. That gives us mu s rg. Now everything in this expression is known. So mu, coefficient of static friction for the tires is 0.84. Radius of the track, okay, from car to the center of the track, this radius is 240 meters. 240 meters. And g is acceleration due to gravity, which is 9.8 meters per second squared. Take the square root of that. And let's do the calculation. See what you get. Didn't bring my calculator. Can you do that calculation? Let's see what you get. Where did m go? We cancelled m here, so we have m on left side and m on right side. So we cancel the m's, so that's why there's no m here. So did you guys have any answer for this? 44.4 meters per second. Okay, so that's the maximum velocity you can have. If the velocity exceeds this one, then the friction won't be able to withhold the car. The car will slide off the road. Okay. So when there is no enough friction, the car will slide off the road. Like when you are driving in like icy road or muddy road, the car goes out of the track. So the friction, that's why the friction provides the centripetal force. Okay. So let's look at number 3.
Can you explain centripetal force a little bit more? Yeah.
What's the confusion?
I just don't really understand that.
So let's do let's see, this problem that will give you more. Okay, so let's see. will help you understand this more. Okay. So let's look at this problem, okay? So we have, let me just copy and paste this one. So we have some kind of object, okay, and it's tied to a string. Okay. Imagine that there is no string, and let's say the object is already moving. Which way the object would go? Imagine that there is no string attached to that object, and the object is moving. Which way will the object go? Straight, yes. Newton's second law. So when there is no force, the object moves straight in a straight path. Okay, it will just move straight. It will move that way. Okay. It will move in straight path forever. But if you pull that object, what will happen? It will remain in this path. Okay. So you are changing its direction when you are pulling it. Okay. So instead of going straight, now it will go in this path. Okay. And when the object is here, it tends to move that way, straight, but you are pulling it inward. Because of that pull, instead of moving it straight, it will change its direction. It will now move like this way. Okay. And again, in this point, at that point, it moves. It tends to move this way, but you are pulling it inward. So each and every point you are pulling it inward, that keeps the object in a circular track. Okay? It's just like gravity. So let me give you the example of gravity from previous chapter. So you have an object thrown straight along horizontal direction, and assume that there is no gravity acting on the object. If there is no gravity, the object will just move straight this way. Okay? But because of gravity, while the object is moving this way, the gravity is pulling it down, so the gravity pulls it down like this, down this direction. So it changes the direction from this straight direction to this one. It still tries to move that way, but the gravity is pulling it down, so it moves this way. Again tries to move that way still, but the gravity pulls it down. Because of that, it moves down. So it traces this kind of like parabolic path because of this gravity force pulling down. But in case of centripetal force, so the object tends to move this way, so the force pulls it down, it changes the path. Okay, it tends to move that way, it's pulled that way, so it changes the path. It tends to move that way, so I don't know why it's doing that. So then because of this inward force, it moves in circular track like that. Okay, and when it's moving that way, so it's again trying to move straight, but because of the force, this inward force, it's still in the circular track. Okay? So because of this circular track, the object remains in the circular, and because of this centripetal force, okay, the object remains in the circular track. It doesn't move away from the center. Okay. And this centripetal force could be different kinds of force. So in some cases, static friction keeps the object in circular track. Okay. Like we saw in the previous problem. In some cases, like in this problem, it's the tension that keeps the object in circular track. So let's look at that. So here, instead of flying off, because of this tension in the string, the object remains in a circular track. Okay? So what keeps the object in the circular track is the tension in the string. Okay, so in this case, centripetal force, which is this one, necessary to be in a circular path or circular track is provided by tension. Okay? So all we need to do in this context is to figure out what is the centripetal force. In this case, tension. In previous one, this centripetal force was provided by this static friction. Okay? That's in the previous problem. And in next problem, we'll see that it will be provided by a different kind of force. Okay? So that's what we want to.
So it just depends on the force. That's what
Yes,
you're
it
saying.
depends on the context. So what context you're talking about. For example, let's talk about Earth and Moon. So you have Earth and Moon. So Moon tends to move in straight path, but because of this gravitational force, the Moon rotates in circular track. So what keeps the object or Moon in the circular track is this gravity force. Okay? So gravity force provides this mv squared over r. Okay, so that's what we want to figure out for all these problems. Okay, so here, let's do the, yeah.
So the forces in the x direction don't equal to 0?
It's not equal to 0 because there is acceleration. Yeah, I think I did interpret it correctly before. But so if I want to write Newton's second law here, so Newton's second law, let's say the object is here. So this force is T, which is pointing inward. Okay. So Newton's second law is force is equal to ma. Okay. In this case, what force we have along x direction? That's T and m, and this acceleration is centripetal acceleration, which is v squared over r. Okay. So that's what this equation is. So there are two ways to interpret this equation. One is through the Newton's second law. We got this equation from Newton's second law. And we can also say that the centripetal force is given by tension. So both results in the same thing. So here we want to find centripetal acceleration and speed. So let's find that. So centripetal acceleration is v squared over r. Okay, that's the formula for centripetal acceleration. And how do we get v squared over r in this equation? I want to get this thing, v squared over r. So what should I do to get that? We divide both sides by m, right? So cancel m and m. Now what is left on the left, you have v squared over r, and that's what we need. So that's t over m. So T, tension is 25 newtons, and M is mass of the puck, 3.325 kg, and that will give you some number. I don't know what the number is. You can find that. And then you can also find velocity, okay, or speed. Can you guys do that? I want to see if you guys can figure out speed or not. Tell me how to find v. Is this is about 75.
76.9.
What's that?
76.9.
76.9. The unit for acceleration is meters per second squared. So how do you find V? We have this equation. AC is equal to V squared over R. So in order to find V, what should I do?
Just gonna have to rearrange the term.
Yeah, rearrange, so multiply both sides by R, cancel R and R, and then take square root on both sides. So you have V is equal to square root of RAC. R is the radius of the circle, which is given. The radius of the circle is the length of the string, which is 0.525. And acceleration is, we just found that, so 76.9 meters per second squared. Okay? So that gives us the speed. So let's look at number 3. So the main problem again here is to figure out what force is providing the centripetal force that is necessary to keep the object in circular track. I'll emphasize this again and again, that our main problem here is to figure out force that provides centripetal force to keep the object in a circular track. Okay. So let's draw the figure for this problem. So the racetrack is curved, so the information is not given here, but the Daytona International Speedway has the inclination of 31 degrees. Okay, so that's something you can add in your problem. So let's say this is the track. Okay. So that's the track. Circular track, and it is 31 degrees inclined. Okay. And the car runs on the track, so that's the car. And the center of the track is somewhere here. Okay. So the track is like that. Okay. I'm not drawing all the track, but center is here. So the car moves in this direction. So now let's draw the free body diagram to figure out the force that provides the centripetal force. So free body diagram, tell me what forces we have here. Gravity, yeah, that's right. Gravity is always vertically down. What else? Normal force, yeah. Normal force is perpendicular to the surface. So this is the surface, so it should be. Let's see if I can draw a straight line. So this one should be perpendicular. that's the normal force. And what else we have? There is also friction, but we will neglect the friction in this case, okay? There's another kind of force that provides the centripetal force. So the center is somewhere here, actually. Okay? So we want to know what keeps the object in this track. So there must be something that is pulling this car towards the center. What is that force? So we showed last time that if this is 31 degrees, then this will also be 31 degrees. Okay? So let's draw x and y axis on the figure. So x-axis would be along this surface. So our surface is that. So this would be our x-axis. Okay? We talked about that last time. We would just use the surface as our x-axis. And this so in this particular case, we can use the surface, but we will not use the surface, okay? So, because the surface won't give us the centripetal force. So instead we would use this as our x-axis. The choice of axis is completely arbitrary. You can choose anything as your axis, okay? It's not fixed. You can choose anything as your axis. So we'll be choosing this as our x-axis. And the reason for that is because this is the direction along which our centripetal force is pointing. So centripetal force is pointing towards the center this way. So if we choose this as our x-axis, then it will be easier to solve the problem. Okay? That's why we are choosing this as x-axis. And perpendicular to that would be our y-axis. We draw a line perpendicular to that. So that's our y-axis. So y-axis is along the width. Okay? So if this is 31 degrees, tell me what this angle would be. If this is 31 degrees, what would that angle be? It will be more, less, or equal? Yeah, this will be 31 degrees. So, this normal force is between y-axis and x-axis. So you guys tell me, what is the y component of this normal force? This y component of the normal force. So we have axis like this, y-axis and x-axis. And we have this normal force. We have this normal force. And we have this angle. So I want this y component for the normal force. So what's that? Yes, n cosine theta, and x component would be n sine theta. Okay, so this component is n cosine theta, and this component is n sine theta. And in this case, this is the force. See, it's pointing along this direction. So this is the force that provides the centripetal force. To keep the car on the track. Okay. So majority of centripetal force comes from this force. There is also a little bit of static friction. We are neglecting that here, but mostly it comes from this force. So that means we can equate n sine theta is equal to mv squared over r. Okay? So centripetal force comes from that. this is the main thing you need to identify in the problem. Once you do that, everything else is exactly same thing, similar to what we did in the last chapter. And we also can write another equation here. So if I write Newton's second law along y direction, on y direction we have n minus w. Along y direction we have this n cosine theta minus w is equal to 0, no acceleration. So that means we can write n cosine theta is equal to w. So we have two equations, and out of those two equations you have to find maximum speed. We want to find this, okay, speed. Now, how would you do that? How do you solve this?
Multiply by r and
Yes, you can do that. R, so you can cancel that and that. And then you get r n sine theta. Okay, you can take m down here and v squared. But the problem here with this is we don't have n given in the question. What to do with that? This is the same kind of logic that we used in previous chapters also. So if we don't have n, what would you do? You would use this equation, right, to somehow get rid of that n. So you can write this as n is equal to w cosine theta, and then plug that in here, and that will give you, let's see what you get. So r, n is w over cosine theta, sine theta over m is equal to v. By the way, this is v squared. So W is what? Mg, right? Sine theta over cosine theta is tan theta. We have M is equal to V squared, right? So we can cancel M and M, and V is equal to square root of Rg tan theta, right? Now if you look at the variables here, all these variables are known. R is known, G is known, and theta is also given. And then you can find V. Okay? So it seems like some people are writing the comments that they are having problem with some of the problems. So we'll do more practice on these questions in the next class. So if you are not sure about the things we did in this class, so don't worry about that. So we'll have more practice, okay? And it'll make things more clear. This is the first time you're learning the new concept, so it's obvious that it's sometimes difficult to understand the concepts, but as you get used to these things, it will be better. So we'll do this next time, okay? So don't worry too much about whether you understood or not.
Plug in the values.
Yeah, so in this you can plug in the values and that'll give you V. So we'll continue this in next lecture, and I'll bring more problems that will help you to give some practice and understand the concept.